That is in general for fluidics in general. Now we work on the micro scale. So now, assume now that we have a, let me take away this. Assume now that I have a micro channel. Let's make it cylindrical. And it's a horizontal channel. It's very small and it's filled with liquid. That means an incompressible liquid. And I have a certain pressure P1 here and a pressure P2 here that is static pressure over it. And we're going to look at, so these are static pressures, and I'm going to let this evolve to a stationary situation. Then my question is, and this is now the next quiz question, I have my formula here with 1, 2, 3, 4 terms here and 2 acceleration terms. Which of these terms will be negligible? Okay, let's look. I have which of these terms are negligible? My pressure gradient, is that negligible? No, it's not going to be negligible. Because it's my pressure, I have defined a pressure gradient here that will drive my fluid, so this is not going to be negligible. Viscous losses, will they be negligible? Well, we know we're going to have laminar flow, so it's dominated actually by viscous losses. So for sure this term is not going to be negligible. Body forces, are they going to be negligible? In microfluidic systems, as I said, it is a horizontal, very small system. Yes, so that's going to be negligible because I have such a small masses. So I will have a very small mass, and also, but not only that, I will have very small height differences. It's a microsystem, and I also said the system is horizontal. So the body force, the pressure gradient generated by the gravity is going to be negligible on a very small system that are laying flat. So this term falls away. The term for compressibility, is that negligible? Well, we said it was a liquid, and liquid is incompressible, so this term is negligible. That's not true if it's a gas system, of course, but for compressible gas. But for liquid, it's going to be negligible. In terms of acceleration, du dt, will I have an acceleration? Well, I started saying like I have a stationary situation. I let this evolve to a stationary situation. That means that there is no change in velocity field anymore, so du dt becomes 0. And I have my rotation term. This rotation term is only important when you have rotating flow. That means turbulent flow. And I'm not going to have turbulent flow, so even this one becomes negligible. So I will see the only terms that actually are matters here is that my pressure gradient must equal my viscous losses. So now I have greatly simplified my formula. Let me rewrite that. I have my formula, pressure gradient plus mu delta square u equals 0. And now actually this is so simple that for such a cylindrical tube, I can actually solve that. Because I know that delta P over P equals, I mean, if this is a length L, that the gradient of this one equals P2 minus P1 over L. Yeah? Pressure difference per length is P2 minus P1 over L. And this here, my second derivative here, well, if I make a cylindrical coordinate system with R here, and I have a cylindrical coordinate system with a length Z here and a radius R and an angle phi here, then I will see that the only, if I take this term here, I can simply write in here as delta, the second derivative, versus R. Because I have no acceleration, my flow field in any position will be the same, it's stationary. So my flow velocity will be the same at any point. If it wouldn't be the same, if my for example, if I consider a point here and I look at my velocity u here, and I take another point here and I have a velocity u that would be different, for example, larger or say a smaller, that would mean that I will have a compressed, I have to compress my or decompress my fluid to get different velocities. But because I have an incompressible fluid, in every point I must have the same velocity. So I know that du dz equals 0 for sure, and of course the whole system is circle symmetrical, so du d phi equals also 0. So the only change I have in velocity gradient can be in the r direction. I can have different velocities at different positions between the middle point and the edge r here of my cylinder. Yeah. And this is a very simple second-hand equation that I can solve if I have two boundary conditions. Which boundary conditions do I have? Well, I have one boundary condition The first is the no slip condition. No slip condition means that if a liquid is in contact with the wall, so this is a solid wall, and here I have a liquid in the tube that is close to the wall or in contact with the wall, a liquid that is in contact with a solid, like for example air over this whiteboard, where the liquid is where the fluid is in contact with the solid, it has to have the same velocity as the solid. Of course, here this whiteboard is standing still, therefore the velocity of the air at the interface must be 0. And I have the same in the liquid here. We call that the no slip condition. And that is in the case in the most fluidic systems, you actually have a 0 slip at the boundary. There are systems where you have a very slight slip, for example, where you have tiny gas bubbles or something, and then the liquid is not really in contact with the solid, and it kind of, But typically in fluidics, you say you have a 0 slip at the boundary, the no slip condition. And that you write as du dr. No, you write, sorry, u at r equals r. The velocity at position r equals r must be 0 everywhere. And the second condition is the one of symmetry. So no matter what kind of flow profile I have, it has to be symmetrical around the axis here. And I express that by saying that symmetry, that in the 0 axis, so u at r equals 0, and actually it's du dr, delta u delta r at r equals 0 must be 0. And with these two, I can simply, I have to integrate this 2 times, and I have the two constants. I get integral constant. I can solve by taking into account these 2 boundary conditions. And if I do that, so I integrate and I integrate once more, I'll be able to solve this and write that u, the velocity r, ur, equals delta p, so p1, 2 minus p1, divided by L times 4 mu times r squared minus r squared. And r, the small r here is of course is the coordinate, the radial coordinate, and the large r is the radius of the tube. And how does this profile look like? Well, I'm going to draw that actually here. So this is my central line. So now I'm going to print my velocity u. I'm going to print u in this direction, and this is of course r. And I have that I have my boundary condition, my no slip condition. So here it's for sure 0, and here it's non-zero, and it's parabolic. I can see that in this formula, so I get a parabolic flow profile looking something like this. So at any point, for example, at this specific distance here, at any point at this distance, for example, in this point here, I know that my velocity is exactly this large. And in this middle point, my velocity is this large. At any, it's the same here and here and here. So on any streamline, it will have the same parabolic flow profile. Yeah? And now I can, based on this flow profile, I can calculate what is the volumetric flow, and I do that by integrating over this area A here. If this area is A, and I integrate my flow over this area, and I can do that, I calculate it, and we get an expression that looks like Q equals delta P times P r to the power 4 divided by 8 mu L. And I hope you can still see that on the video. Yes? So I see the flow and the pressure are linearly related. So this is like a cylindrical channel, or basically any laminar incompressible flow channel will work as a fluidic resistance for a certain pressure difference, which could be the same as like an electrical potential, will give you a current, which here in this case is a hydrodynamic flow Q. And then this is the fluidic resistance of this system. It's PR to the power 4 times 8 mu L. And now what I see, what is important is that my volumetric flow rate will scale with the 4th power of the radius. So I may take a little tube and I make it 2 times smaller. For the same pressure difference, I'm going to get 16 times less flow through it. So that's extreme. So you see, downscaling a fluidic system, the flow throughput will become extremely small very fast. And actually I also can use this to calculate an average velocity u, and you can do that at home if you like, for yourself, and you can see that scales actually with the r square times delta p over L, and there's a factor 8 mu here. So the average flow velocity scales with the 2nd power of the r, and the volumetric flow with the 4th power of the radius. So we'll see in microscales we have very little flow throughput and very small flows.